1. Alright, so suppose that you do indeed have a Riemann integrable function. I want to show that now given an epsilon. Things work out the way we want them to. Alright, so note that the Riemann integral is both the lower and upper Darboux integral, which means that it's the infimum of the upper Darboux sums. So since it's the infimum, if I were to push it forward by a little bit, there is a upper Darboux sum that is strictly less than it. And similarly, we can pull the same move with the lower Darboux sums, because the soup of the lower Darboux sums gives me the lower Darboux integral. Alright, and hey, I have two things, so I've got two epsilons, and I have two partitions, and now note the move that we've already pulled. Combining them together gives me a partition that's bigger than both, and making a bigger partition increases the lower Darboux sum and decreases the upper. So the upper on P is less than the partition here on R, right, because I added, right, P is contained in R here, and this was then chosen, of course, to be less than that. Right, other way around, sorry, I think I said P. R is contained in P, so this one gets smaller. And then, hey, we know that this is less than that plus epsilon, and T, of course, contains P, so the lower one gets bigger. And hey, there we go, subtracting it over gives me the upper Darboux sum minus the lower is less than epsilon. So conversely then, given an epsilon, suppose we can find partitions where the upper and lower Darboux sums behave. Okay, so I want to prove that I'm integrable. Let epsilon be greater than 0. By assumption, I need to have this partition. Now, where does this partition have to live? Well, of course, it is a element of the collection of lower Darboux sums, which means it's less than or equal to the soup. The soup there is less than or equal to this inf. This inf is less than or equal to this. The upper Darboux sum, which is the infimum of the upper, so we know we've got that. So the difference of these is greater than or equal to 0, and bounded above by the difference of these, and those are arbitrarily small, which means that these things have to be arbitrarily close. In other words, they have to equal each other, and thus we're integrable. Alright, sweet. Now, something you may notice here is, alright, well, I did this for any epsilon, but man, it'd be great if I had, like, you know, a sequence or something. Alright, so a collection of partitions for a function will be called an Archimedean partition, or an Archimedean sequence of partitions, if the limit of the upper and the lower tends to 0 when we take that difference. Hey, note that by the previous result, we basically immediately get that if you are Riemann integrable, you have to have an Archimedean sequence of partitions, and conversely, if there's an Archimedean sequence, you have to be integrable, right? Because we already just demonstrated that Riemann integrability is the upper and the lower Darboux integrals are behaving, and specifically the upper and lower Darboux sums are behaving. And here, we get this result, which the power here is that this actually now gives us a direct way of computing the Riemann integral, using a sequence of things. Ooh, all right. So first, let's unpack this proof. And let's note that this is really just a repackaging of the previous proposition. If we're Riemann integrable, then we know that for any epsilon, there are partitions so that the upper and lower Darboux sums are with an epsilon. Okay, well, 1 over n always works. And note that as you take the limit as n goes to infinity, that goes to 0. So that's an Archimedean partition. Similarly, if you have an Archimedean sequence of partitions, given an epsilon, this limit is 0, so at some point they get smaller than epsilon, so given epsilon there is a partition where things work, and thus you're Riemann integrable. Great. Now, the key thing, the extra piece of this proof that's extra important is that the limit of these Archimedean partitions will give us what we want, because that's the power there. So now note, previously, we haven't exactly gone, well, the upper Darboux sums or the lower Darboux sums actually, like, you know, give us something. So let's actually do that. so note for any n, we know that the lower Darboux sum of the nth partition here will be less than or equal to the Riemann sum, and likewise for that. And now, when I look at the absolute value of the differences of these things, well, note that they're going to have to be stuck bounded above by these. Right, so if we look at this minus that, well, it'll be that minus that, and likewise for this one. And as we let n go to infinity, these things go to 0, which means these sequence of lower Darboux sums and sequence of upper Darboux sums will actually coincide with the Riemann integral. All right, now this actually gives you a way of computing Riemann integrals. Now, of course, it's the limit definition, which is not the way we really actually compute these things. We normally go for antiderivatives, but let's look at the function f of x is equal to x. We know its antiderivative is x squared over 2, and if you integrate that from 0 to 1, we know we should pick up a half. But let's actually see how you can do this using an Archimedean sequence of partitions. So, given an n, we'll define the partition on 0, 1 to be the usual one you would do, the one that's equally spaced. Right, when k is 0, we get 0. When k is n, we get 1. So it's just cut up the domain into equally sized pieces. So note all the delta x's are in fact 1 over n. Nice. All right, so then the infimums and the supremums are easy to compute. This function is increasing, so the infimum is the, hey, look, left endpoint, and the supremum is the, hey, look, right endpoint. Hey, great. So then when we go ahead and compute the lower Darboux sum, it's just the typical left-hand Riemann sum here. Yay, and note it will clean up to n minus 1 over 2n. Note here we're using the very famous, if you add up a collection of consecutive numbers, you get n times n plus 1 over 2, but note here it's k minus 1, so you'd get n minus 1 and n. And note we pick up this n squared from here there's a 1 over n, and the left endpoint has the n, and hey, look at that. Now we've got the lower Darboux sums, which again were turned into a traditional Riemann sum. You can do a similar thing for the upper, and when you take their difference, you hilariously get 1 over n. Oh, look at that. Isn't that wonderful? So we've got an Archimedean sequence, so we know we're Riemann integrable, and furthermore, the limit is in fact the thing we know it to be, which is 1/2. Beautiful. Actually, there we go. We actually computed a Riemann integral, and we did it with limits. Pretty cool. All right, and of course, now we geometrically can argue this because if you actually draw this out, it's just a rectangle, so with right base and height of 1, so pretty easy to compute. But at least we get this right. So here we've got a very explicit limit argument for the area of that triangle. It's 1/2. Cool. All right. Well, speaking of classic Riemann sums, I just saw them in action. Right, but that was kind of a specific case where it just so happened to be that the lower and upper Darboux sums gave me traditional Riemann sums. So naturally now I want to go, well, I learned all that crap in calculus, like, does it still apply? Does it still exist? And it does, but as we were going to see, it will exist, it will work, and everything will be great, but the actual details here for Riemann sums gets, it gets fun. All right, so let's do it. So, given a partition, we'll create the Riemann sum by doing exactly what we would normally do. You cut up the domain into these subintervals, you make your rectangles, and the heights of those rectangles are the function evaluated at any point, I don't care which one. Now, of course, as is tradition, we normally do a lower or an upper or a midpoint, but it really doesn't matter which point you pick. Sometimes one does better than the other, depending on what function you're looking at. All right, but let's actually now connect this traditional Riemann sums to the Darboux sums we've been working with. So in particular, take a function, take a partition, and then we'll look at the collection of all possible Riemann sums that you can make. So note, these are the Riemann sums where, right, I'm just going to go ahead and pick any random points, and the infimum of all possible Riemann sums for a partition, in fact, is the lower Darboux sum. And likewise, the upper Darboux sum is in fact the supremum of all possible Riemann sums. So here we see the connection now finally of how Riemann sums will relate to the lower and upper Darboux ones. They are precisely the imps and the sups of all possible things. So, pretty cool. All right. Now, let's go ahead and work out the details of that proof. And as always, I'm only going to do the first one, and note that the other one is flip the sups to imps. The other way around, flip the imps to sups. Okay. All right, so first thing to note, if you're looking at the lower Darboux sums, you're looking at the infimum of your function on every subinterval, which is always less than or equal to just, the function evaluated at any point, which means that clearly the lower Darboux sum is always less than or equal to any Riemann sum, right? We already pointed that out, right? That this Darboux approach is basically going, well, let's ignore the picking point thing for a moment and work in extremes. And indeed, yeah, the lower Darboux sum is in fact the lower bound for the collection of all Riemann sums on the partition. Now we actually need to prove that it is in fact the infimum. So this set is bounded below, so it does have an inf. Now I actually need to prove that the inf is in fact what I want it to be. All right, well, suppose that the lower sum actually is strictly less than. Hey, that gives me an epsilon to work with. Isn't that great? Well, now what? Well, given an epsilon, if I push this forward by an epsilon, and in particular I'm going to pick epsilon over b minus a, if I push this infimum forward, that means I can find points out of the domain so that my function does not is strictly less than it, right? If I push the infimum forward, there are things you can find that are less than it. And then now, hey, what happens when I add all of these up? Well, when I add them all up, we know that any of the Riemann sums is less than or equal to alpha. Alpha here is the infimum of all the possible Riemann sums. But these these Riemann sums were chosen so that these are always less than that. And if we clean this up here, distribute the delta x, here you'll get this sum, which is the lower Darboux sum. And here, when you add up all of these, oh, well, you get epsilon. But as we already demonstrated, epsilon is equal plus the lower Darboux sum equals alpha, and then we've got alpha is strictly less than alpha, which is contradictory. There you go. So indeed, the Darboux lower sum is in fact the infimum of all possible Riemann sums. Good stuff.